Hey pre-calc students, in this video we're going to talk about polynomial division and complex solutions. We're going to talk through how do we divide polynomials, and then how can we use division to find complex and imaginary solutions to polynomials, also known as roots, and then also talking about operations with some complex numbers. So the first thing is we need to review our long division skills that we learned back in 3rd grade. So I want to take the number 452 and I want to divide that by 3. So the first thing I'm going to do is I'm going to set up my division sign. And I'm placing the 3 outside my division, and I'm placing my divider, what I'm dividing into, inside my division house. And for these problems, we're always talking about how many times does the outside number, how many times does this outside number go into each place value. So I can take 3 and I can divide it into 4, and really I'm dividing it into 400. And so again, all I'm doing here is I'm seeing, and a little bit of scratch work off to the side, I'm going to see how many times can 4 be divided by 3, and I'm going to reduce that as much as I can. Well, it can go in 1 time. So then once you have how many times 3 can go into 4, our next step is to multiply. So step 1 is to divide. Step 2 is to multiply, because I've taken 1 3 out of that 4, so I'm going to say 1 times 3 is 3. And then I'm going to subtract away, essentially what I've done is I'm saying 3 goes into 400 100 times. So I'm taking 300, essentially 300, but just using the place underneath the hundredths place. And I'm going to take that away. So step 3 is to subtract. 4 minus 3 is 1, and I'm going to bring down my tenths place, 5. So now I'm going to repeat my step. So I guess step 4 is to bring down. And then I'm going to repeat. So how many times does 3 go into 15? Well, it goes in 5 times. So I'm going to do 5 times 3 and get 15. Take that away. That will cancel, leaving me with 0. I'm going to bring down my last place value, which is my tenths place. So then the question is, how many times does 3 go into 2? Well, it doesn't go in evenly, so this is going to be my remainder. And for the purpose of this class, we're going to write remainders as fractions. So my remainder is 2, and so I'm going to have 2/3 left. Again, the remainder, 3, what I'm dividing it by, I have a 2/3 remainder left. So 3 goes into 452 15 and 2/3 times, and that is division with numbers. So the purpose of reviewing long division with numbers is that we also want to be able to review long division of polynomials. This is a skill that is covered in Math 3, but I will go through the process of dividing polynomials. So the first thing I'm going to do is I'm going to write out my steps. And I'm also going to set up my division symbol where I'm dividing the polynomial 3x cubed plus 5x squared plus 8x plus 7. And I'm dividing this by the linear polynomial 3x plus 2. Okay, so I'm going to do each one of my steps, and then we'll talk through. So the first step is to see, and we always use our very first term. So we're going to see how many times can a linear 3x go into a 3x cubed. The best way I can explain this is that we're actually doing division here. So I'm essentially saying 3x cubed divided by 3x, and I'm going to reduce that. If I reduce, my 3 divided by 3 is 1. And my x cubed divided by x, well, I'm going to reduce my exponent. When you divide exponents, you subtract them. So 3 minus 1 is x squared. So 3x goes into 3x cubed, 1x squared times. Okay, once you have your division, Then you want to multiply. I'm going to change my color here, and what I'm multiplying is going to be whatever I got in my divisor, so 1x to the second power, and I'm going to multiply all of that times my 3x plus 2. And I'm going to write that below the polynomial that I'm dividing into. So 3x cubed when I multiply, and then 1x squared times 2x is 2x squared. Okay, once you have multiplied, my next step is to subtract. And that is a positive 2x, so I should have a plus sign there. Now, the biggest mistake that people make when they're subtracting is that they will forget to subtract all terms. So put it in parentheses so that you remember, but I'm doing 3x cubed minus 3x cubed. If you're doing long division of polynomials correctly, this first term will always cancel each other out. So 3x cubed minus 3x cubed cancels. And then 5x squared minus 2x squared is going to give me 3x squareds. And then I'm going to bring down. And then my goal is to repeat this process until I have no ability to divide. So again, going back to division, I'm going to divide my 3x squared now, divided by, well, I'm dividing it by 3x. Again, I want to reduce. 3 divided by 3 is 1. X squared divided by x is x to the first power. So this is a 1x, and I don't have to put the first power. So my next term is going to be this linear 1x. Okay. Once I have divided, I'm going to multiply. So I'm going to take this 1x and multiply it by my divisor, 3x plus 2. After I multiply, I want to subtract. Again, if you're doing this correctly, this first term should always match so that when you subtract, you will always cancel those out. And then I have 8x squared, or 8x minus 2x, which will give me 6x. And then I'm going to bring down my plus 7. Okay? And then repeat the process again. So I have my next division is I'm taking that 6x and I'm dividing it again by my divisor 3x, and I'm going to reduce this. The x's will cancel each other out, and 6 divided by 3 is 2. So that gives me a 2 in my constant term. Then I'm going to multiply, subtract. And then if I were to try to reduce this, I've gotten to the point where if I were to try to simplify this, if I were to try to do another division, 3 divided by 3x, this can be simplified, but what we're always trying to do is we're trying to divide the polynomial piece, right? So on the top, I have a constant polynomial, meaning no x's, and on the bottom, I have a linear polynomial. So once you get to the point where your divisor has a bigger exponent than what you're dividing by, this is considered your remainder. So my remainder for this polynomial is 3, and I have 3 over 3x plus 2 is my divisor. And because this is a polynomial, I always want to link all of this with addition or subtraction. So this is my final polynomial that I get when I divide. In fact, this is no longer a polynomial because of this piece right here, but we'll talk more about that when we do rationals. Right now, we just want to talk about dividing two polynomial terms. Okay, let's do another example for this problem. We're going to set the problem up together. Then I'm going to do the first step with you, and then I'm going to see if you can do the remaining pieces on your own. So to set up, we're dividing the polynomial 3x cubed minus 2x squared plus 4x minus 3, and I'm dividing this by a quadratic polynomial plus 3. X squared plus 3x plus 3. Okay, so for our first step, we're going to divide, and just a reminder, whenever we're dividing, we're only looking at the first term that you're dividing into divided by the first term of your divisor. So I'm going to take 3x cubed, and I'm going to divide that by x squared and see if I can reduce this. This reduces to 3x. So that's what's going to go on top of my divisor. Next step is to multiply, then subtract, bring down, and repeat. See how much of this problem you can do on your own. Pause the video. Okay, check in with your work. When you are subtracting, we have a negative 2x squared, and I'm subtracting a 9x squared. Be careful, make sure you are subtracting. So this will give me a negative 11x squared. 4x minus 9x is a negative 5x. Okay, keep working. Talking through our subtraction, we have a negative 5x minus a negative 33x. The minus negative becomes like a plus positive, so this is going to be 28x. And my negative 3 minus negative 33, and negative 3 minus negative 33 is going to be a positive 30. At this point, if I were to try to divide 28x, which is linear, divided by x to the second power, which is quadratic, this is no longer reducible. Linears are a smaller degree than quadratics, so this is my remainder. So I'm going to write my remainder. You write your remainder as a fraction where what you're trying to divide into is on top, and what you're dividing by is your denominator. Okay, pause the video if you haven't already done so and check your work and see what questions you have. Okay, for this next problem, I want you to try this one totally on your own, and I will show work and speed it up so that way you can check the work that you're doing. Okay, the trickiest part about this problem is that when you multiply, the like terms actually skip a place. So here I have this x squared. I don't have an x, and then I have a 4. So when I've got, when I'm trying to subtract, you want to make sure you're only subtracting like terms. So I do have, for instance, when I multiplied my first divisor, 2x, to the second power, and I multiplied it by x squared plus 4, that gave me 2x to the 4th plus 8x squared. So I lined up my like terms because when I multiplied, I did not actually have an x to the 3rd power. So again, I skipped unlike terms, and when I subtracted, I just made sure I lined up my like terms so that they would subtract. When checking your work, the easiest way to do that is if you have the same remainder as me, then you probably did all the work correctly. But look this over and see what questions you have. Okay, so really quickly we're going to take a break from the division of polynomials so that we can talk about imaginary roots. So you've seen this before with quadratics. Quadratics can have imaginary roots. For example, the quadratic x squared plus 4 will have imaginary roots. There are two ways that you can find your imaginary roots. You can set it equal to 0 and solve, or you can use the quadratic formula. I'm going to set it equal to 0 and solve. So I've got x squared plus 4. This can't be factored, but I can set it equal to 0. If I subtract 4 from both sides, I have x squared is equal to negative 4. If I take the square root of negative 4, this will lead me to imaginary roots. So the roots that I would get from this is plus or minus 2i. So the negative is where the I comes from inside the square root, and the square root of 4 is 2. So this would give me two solutions, or two roots, 2i and negative 2i. Normally roots show up on the x-axis, and so this is what I would be finding, but here this quadratic has imaginary x-intercepts, so this quadratic actually does not cross the x-axis, but it still has roots. They're just not on the x-axis. If I were to graph this quadratic function, it would be a U shape starting at 4 on the y and go up. So this doesn't have any x-intercepts. So that's where we say these roots are imaginary. So you've seen quadratics with imaginary solutions. What long division allows you to find are higher power polynomials, roots, real and imaginary. So we're going to do an example of that. Okay, so how we can use the concept of imaginary solutions or imaginary roots with our higher polynomial powers is we're going to use the graph to find the real solution. So the real solution is going to show up as an x-intercept. We're going to turn it into a factor. Then we're going to use long division to divide away the factor that creates the real 0, and we'll solve the remaining quadratic. So the first thing that I'm going to do, I have an example, f of x equals x to the third minus 2x squared plus 20x minus 40. First thing I'm going to do is graph and find all possible real solutions that I have. Okay, so here is my graph of my cubic polynomial. I can see that it kind of looks cubic. It crosses the x-axis at 2, 0, giving me one real solution. So one of my solutions, or one of my roots to this equation is 2. So x equals 2 is a root. And so what I want to do is I want to think about the factor that came from. So we want to get 0 on one side. And this is the 0, this is the factor that the 0 or the root came from. So what this means is that f of x can be written in some kind of factored form. One of the factors can be x minus 2. And the other factor, I don't really know what it is, so I'm going to put a blank space and I'm going to see if I can find what that factor is. Well, if I want to find what two things will multiply to give me this function, I can use division to find this missing piece that is being multiplied. So I'm going to set up my division, and I'm going to do all my division work sped up really quickly once we get it set up. So I'm going to take my factor that I do know exists and divide that into the polynomial that has that factor. I'm going to do all of this work and then speed it up, so pause the video and give this a try on your own. Okay, so in my division, I got that x minus 2 goes into my polynomial x cubed minus 2x squared plus 20x minus 40, x squared plus 20 times. So that would mean if I were to multiply back out this factor and this factor, I would get what my original polynomial that has been multiplied out. So what I've now done is I found a factor, x squared plus 20, and I can write my original polynomial, f of x, using the factors x minus 2 and x squared plus 20. I know that these are factors because I have no remainder. And anytime you're dividing and there's no remainder, that means it is a factor of whatever you're dividing by. Well, we already have the solution from this factor. We already have the root here, right? The root was x equals 2. And I can use this factor and find the remaining imaginary roots that are not showing up on the x-axis. I'm going to solve this by setting it equal to 0 and solving. The square root of 20 is about 4.5, so I changed my equal sign to a estimate equal sign, making it squiggly, or I can leave it if I want. I can say I times the square root of 20 or negative I times the square root of 20 if I wanted to leave it to where I'm not rounding my values. So this cubic has 3 roots. It has 2, and it has I times the square root of 20 and negative I times the square root of 20. anytime you have a polynomial, the degree will always match the number of roots. So here we have a cubic, and the cubic will have 3 roots. Not all of them will be real, right? Some of them will be real and cross the x-axis, and some of them will be imaginary roots where it does not cross the x-axis. The last thing that we'll cover in this video is just some operations with these imaginary numbers. So we call a number complex if it is a combination of an imaginary number and a real number. You can add and subtract complex numbers by combining like terms. My example is I have 4 minus 2i minus 3i plus 1, and I can combine these. The first thing I'm going to do is make sure I am subtracting both the 3i and the 1. So this is the same thing as 4 minus 2i minus 3i minus 1. And then you can combine your like terms. Your i's, or imaginary parts, are like terms. So negative 2i and negative 3i can combine to negative 4i, or sorry, negative 5i. And I can also combine my non-imaginary or my real parts. 4 and negative 1 can combine to 3. So this would be negative 5i plus 3. The other thing that we can do with imaginary or complex numbers is to multiply them. The only thing that is important to remember is when you take I and you square it, that's the same thing as taking the square root of negative 1 and squaring it, which would just give you a negative 1. I'll show you that in the example. So to multiply, I'm going to distribute. 4 times 3i is 12i. 4 times 1 is 4. Negative 2i times 3i is going to be a negative 6i squared. And then negative 2i times 1 is negative 2i. And then I want to combine like terms where I can. So I see I have a 12i and a negative 2i, so I'm going to combine that. I'll combine this into 10i. I still have my plus 4. I still have my minus 6i squared. Now I'm going to focus just a moment on this I squared. So where I comes from is it comes from the square root of negative 1. So I'm going to replace that for just a moment. Again, all I've done is I've just replaced I with its definition, square root of negative 1. And I notice that the square root and the square will cancel each other out. So this is the same thing. I'm going to rewrite everything else. So this is the same thing as instead of 6 times the square root of negative 1 squared, this is the same thing as 6 times negative 1. And then I can continue to simplify from here. And I can combine 6 and 4 to 10. So this is 10i plus 10. Great, we will do more practice with all of this tomorrow in class.